an HTM-based update side synchronization for RCU on NUMA systems. This work is done by I, Sungjae Park at Amazon, Paul E. McKinney at Facebook, Laurent Dufault at IBM, and Han-Wai Yum at Seoul National University. Disclaimer: this work was done prior to the first author joining Amazon and while the second author was at IBM. The views expressed herein are those of the authors. They do not reflect the views of their employers. More than a decade ago, the world has changed to multi-CPU era. Nowadays, huge NUMA systems utilizing hundreds of threads are common. Therefore, efficient synchronization primitives are the key of performance and scalability. The read copy update is a synchronization mechanism for read-must workloads. It is well known that it provides almost ideal performance and scalability for reads. Let's show how this works using an RCU protected linked list as an example. In case of the reads do nothing special except notifying its start and completion here. Those can just traverse the list. For the updates, let's suppose that we want to delete the item B here. The RCU updaters should first lock and then update the next pointer of the item A to item C and then unlock. The lock is required to avoid the race between concurrent updates. Therefore, use of the global locking here could become a scalability bottleneck. After this update, now there are pre-existing readers and new readers. The pre-existing readers can still access to A, B, and C, while the new readers can access only A and C now. Then the updater waits until the pre-existing readers complete. After the completion, now nobody can see the B. Therefore, it's safe to deallocate and reuse the memory region of the B. This is called quiescent state-based reclamation. So, the RCU doesn't provide the update side synchronization by itself. This lack of the RCU-centric update side synchronization is an intended design that aims to allow users selecting or implementing best synchronization mechanism for them. However, many users use the global locking here because it's very simple to apply. However, as above mentioned, this can impose scalability problem. To mitigate this problem, several RCU extensions have proposed before. In SOSP 15, read log update has proposed. This mechanism adopted a software transition memory-like logging mechanism for updates. Let's see how this works using an RLU protected linked list as an example. In case of reads, the RLU reader is required to find a proper version in addition to notifying its start and completion. For updates, let's assume we want to delete B again. In this case, the RLU updater should create a new version of A which points the item C as the next item, and it should protect the creation of the new version using RLU lock critical section. The critical section is similar to software transition memory transactions. If it conflicts with others, it aborts by itself. Therefore, the reader updater conflict is avoided here because readers can search valid versions by themselves. For example, in this case, the new readers will first reference the A, but it will know that the A is old version and therefore it will go to A-, which is the new version. After this change, the updater will wait until the pre-existing readers complete again, and after that, the updater swaps the new version of A and old version of A so that the readers can now access new version of A and C without referencing the old version of A. Therefore, it will be safe to deallocate and reuse the memory regions of the A and B. Therefore, it can deallocate. After this, in Pact 17, RCU HTM has published it. It encapsulated each update in an HTM transaction. Let's show how it works using an RCU HTM protected linked list here. The readers do nothing special except notifying its start and completion, just same to that of the RCU. In case of the update, the RCU HTM should protect the update with the HTM transaction. In other words, the RCU updaters should encapsulate the data update within HTM transactions so that the HTM can guarantee consistency and scalability by themselves. else assign to QSBR, wait until safe to delocate and deallocate. With this state-of-the-art scale on NUMA machines, both RLU and RCU HTM had not evaluated on huge NUMA machine, but on single-circuit machines utilizing 16 threads and 44 threads only. Therefore, we prepared a evaluation server utilizing 4 circuits. In each circuit, there are 18 physical CPU cores, and hyperthread is enabled. Therefore, in total, there are 144 hardware threads there. Also, please note that every following evaluation also uses this machine. For evaluation workload, we use random reads, insert, and delete to kernel space linked lists, which are protected by RCU, RLU, and RCU HTM. We also populate 256 initial items to provide sufficient data parallelism. The evaluation results are shown here. As you can show, unexpected poor scalability has revealed. The RLU imposed significant overhead to read, and with updates, both RLU and RCU HTM degraded the performance as multiple NUMA nodes being started to be used. What are the root cause and implications of the research? RLU's read overhead apparently comes from the valid version searching. The read-mostly performance-sensitive workloads would not be able to easily use the RLU instead of RCU. And the NUMA oblivious designs of RLU and RCU HTM degraded the update scalability. Especially in case of the RCU HTM, amplification of HTM aborts on NUMA machine impacted the research. In detail, the long latency between NUMA nodes makes transaction time long and thus is to be aborted, and the dominant number of readers conflict with HTM transactions of update threads and abort them. Nonetheless, the HTM benefit is clear. Therefore, we need NUMA-aware HTM use for read-mostly workloads. To this end, we designed new RCU extension called RCX with our principles. First, do fine-grained update-side synchronization. Second, use pure RCU read mechanism for the ideal read performance and scalability. Third, use HTM. Only HTM provides hardware-oriented high performance. Fourth, access only NUMA local data objects within HTM transaction, otherwise overthreads exponentially increase. Finally, isolate the HTM working set from the dominant readers because the readers can abort HTM transactions otherwise. This is the interface of the RCX. The readers are same to that of the RCU. Those do nothing special except notifying each start and completion. And the update of the next pointer of the items should be protected by the RCX log. In other words, in RCX, the update critical section should specify items to update inside. Else assigned to QSBR, wait until safe to deallocate and deallocate. Let's show how it works in detail. Each object protected by the RCX log embeds node local logs and a global log. The updaters first acquire the per node local log of the object that they want to update using hardware transaction memory. Once it acquires the node local log, it commits the transaction and then acquires the global log of the object using spin log. The updaters who acquired both local log and global log can update items now. Is the RCX fulfills the principles? Let's show. RCX competes with threads accessing same objects only, therefore fine-grained. It uses pure RCU read mechanism and HTM. And RCX accessed only NUMA local data objects with an HTM transaction and isolates the working set of HTM from the dominant readers, as the HTM in RCX touches only local logs, which is invisible to readers. Evaluations. We evaluate the performance of RCX using the linked list, which I ably described. The evaluation results are as you show here. The RCX performs and scales best for both read-only and update mixed workloads. The similar research has shown with hash tables. We further applied RCX to systems having scalability problems, including the virtual memory management system of Linux kernel and the in-memory DBMS. Linux protects each VMA tree with a global reader-writer lock called MFSAM. Two similar RCU approaches for this problem has proposed, RCU-VM and SPF. However, both approaches could not give benefit to VMA tree update intensive workloads. Therefore, we further applied RCX on top of SPF and called it RCX-VM. This is the performance result of the virtual memory scalability systems. As you can show, the RCX-VM further improves the Metis and EBG workloads. In case of the Metis workload, RCX-VM showed up to 24 times higher performance compared to original and 2 times higher performance compared to SPF in 144 thread case. With EBG workload, it showed up to 5 times higher performance compared to original with 72 threads and showed 2 times higher performance compared to SPF with 36 threads. In case of the P-search and EBG, there was no benefit. This is due to the fact that the bottleneck here is the TRB flush, which is not covered by RCX-VM. The Kyoto Cache DB, the popular in-memory DBMS, uses global read-write lock. We implemented 2 variants substituting it with fine-grained RCU and RCX for this region. And with 20 million records evaluation, the RCX showed significant improvements. In case of the 10% updates, the RCX alternative showed up to 17 times higher performance compared to original and 1.3 times higher performance compared to fine-grained RCU. Conclusion: the RCX achieves best update while preserving the almost ideal read in terms of performance and scalability owing to its NUMA-aware use of HTM. Many details and additional things are in the paper, including detailed investigations of state-of-the-art, including on HMCS lock and RCX variants, and optimization of RCX for memory efficiency and HTM implementation details. Finally, the source code is freely available at GitHub. Thank you for listening.